Section 1.3 looks at combining like terms. So before we start doing any examples where we're actually combining like terms, we're going to look at the definition of like terms. We're going to talk about why we use them, some non-examples, some examples, and then we'll get into some practice. So first, to start, I'm going to start with what the definition of like terms are. So like terms are terms that have the same variable and exponent. So pieces that have the same variable and same exponent. So we want it to have the same letter and then the same numbers on that letter. So same letter and then same power. We do this, we're going to combine like terms before we start solving equations. What we're getting into in the next section will be solving one-step equations. So before we get into that, we need to talk about like terms. We combine like terms in order to simplify the question or the equation before we solve it. So we put together all the pieces, combine like terms, so that we simplify the expression before we can solve, or the equation before we can solve. So we use like terms and combine like terms to simplify sides of the equation before solving. And this makes our life easier if we combine like terms. We don't have to keep track of as many things. Everything's being combined, and then we can simplify. So here are some examples. So for A, remember if there's not, maybe you haven't seen this actually, I don't say remember, but if there's not an exponent written on a variable, the exponent is really A1. So this is really 4A to the first power and 2A to the first power. Notice they have the same letter, they both have A's, and the A's are both to the first power. So these have the same variable, which is A, and the same exponent, which is 1. Those are, in fact, like terms. 6xy and 3yx, do you think those are like terms? They are, in fact, like terms because we have the same variables, an x and an x. They both have exponents of 1. And then our y's also both have exponents of 1. So same variables, same exponent. So these are in fact, and here's y. I'm going to put over here, draw a little arrow. You're going to have to add this little bubble box up here. This is why this is the case. We just reviewed some properties and we looked at the commutative property, which says we can change the order in addition and, I shouldn't do a slash, and multiplication, and the value stays the same. So if it helps you to remember, think of CO in the start of commutative and CO in the start of change order. So the only thing that's different from 6xy and 3yx is that the x comes first in 6xy and the y comes first in 3yx. But I could easily write this as 3xy, and now they are definitely, without a doubt, like terms. They still are in the original question up here. It's just easier to spot when you rewrite the variables from highest to lowest or in terms of alphabetical order. Look at the next one, 2c squared d and 5c squared d. The c's are the same variable that both have 2's as exponents. And then I'm looking at d. The exponent on the d is a 1. Remember, if there's not an exponent written, we assume that it's a 1. So those are some examples of like terms. Here are some non-examples. 7a and 5b do not have the same variable. Even though they both have exponents of 1, they don't have same variable. So I'm going to write a note here so I know different variables. Seven x squared y and 3xy squared. Well, my variables are the same. I have x's and I have y's, but if you notice, this x has a squared, whereas this x has a 1. So I have the same variables, but then different exponents. It would be the same even if this was a squared here. All my variables have to have all the exact same exponents. If one matches and the other one doesn't, it doesn't matter. They have to be exactly alike. So this one, we have different exponents. And my last one, 3 and 3c, I'm looking at a constant right here without any variable, and then 3c, they don't have the same variable and they don't have the same exponent. So different, this one doesn't even have a variable, different variable, and exponent. So those ones definitely are not like terms. So let's look at some practice, this last bubble down here. I have 7x plus 3x. This is really 7 x's lined up, and then 3 x's lined up. And it's asking us how many x's do we have all together. All we're going to do is add these coefficients because the middle operation is add. So really the answer here is 10x. I have 10 x's. Notice it did not become 10x squared. So that's not what I started with. When we're combining, your exponent should not be changing. So 7 x's plus 3 x's leaves me with 10 x's. When you're doing, if you're doing this on Notability, a great way is to change colors and underline. Notice that these both have x's to the first power, so those are like terms. This one over here, 3x squared, has an x, but the exponent is different on that variable, so that is not a like term with the 2 x's. So I have 2x plus 2x, which leaves me with 4x. I'm going to put a green under so I know where that came from. And then I don't have anything else to pair up with that 3x squared. So it's just plus 3x squared. And I just carried that over because it didn't have any other like terms to combine with. Not everything has to have a like term. You can just leave it be if there aren't any like terms. And our last example in this bubble, negative 5ab squared plus 2b squared a. Remember what we said up top? There's a property that lets us rewrite this as 2ab squared, and that property is the commutative property. And so I have negative 5ab squared plus 2ab squared. So I just do the operation with their coefficients. Negative 5 plus 2 is negative 3ab squared. I just bring over the variable and the exponents exactly as they are. The term on the end, I just leave it as is. All I do is operations with the coefficients. So I should have said this to start. It might not have been a bad idea to fill in your bubbles before you get started, or write on the top what you're filling in just so you can go after. But here it is if you need to pause this page and copy everything down that we just went over. So now I'm going to do a few examples. Some of them are pretty easy, some of them are a little trickier. I'm going to start with number 3. Again, if you're doing this and you're not doing it on Notability and need a way to differentiate, do different kinds of lines. You can do shapes, so you could circle your like terms of n and 9n, and then do a square, a triangle around negative 10 and negative 3. The sign out front goes with the number that comes next. So, and also if there's a no coefficient, we assume it's a 1. So 1n plus 9n leaves me with 10n. And then negative 10 minus 3 leaves me with negative 13. So my final answer here is 10n minus 13. I'm going to look at doing number 13. I'm asking myself, same variable, same exponent. So 12r and 3r have the same variable and the same exponent. I'm going to combine like terms here, so 12r plus 3r leaves me with 15r. And then I have positive 5 and negative 5. Well, positive 5 minus 5 is going to leave me with 0. I can, if I want, I can write plus 0, but I don't need to do that. And so my final answer is just 15r. I'm going to get down on the next page almost to the bottom I'm going to do number 30, where we have to do some distributing before we can combine our like terms. So hopefully we've all seen the distributed property before. I multiply negative 7 times n and negative 7 times 3. And then I'm going to multiply negative 8 times 1 and negative 8 times 8n. So up front I have negative 7n minus 21. Watch your signs. And then I have negative 8 minus 64n. Notice I did not touch the exponents on my variables because there was no exponent on the numbers that were out front of the parentheses. They were just constants. So now I can combine my like terms. I had to get rid of the parentheses first. So I have a negative 7n and negative 64n. And that leaves me with negative 71n. And then I have a negative 21 and a negative 8, which leaves me with a negative 29. So my final answer is negative 71n minus 29. I think you'll find that this is kind of easy to get a hang of what you're really looking for. Same variable, same exponent. We're going to look at ones that are a little trickier, like the ones we saw up here where you have multiple variables with different exponents. But for now, what you really need to know, this is your definition that you're really looking at. They have the same variable and the same exponent. And you want to be able to be really strong in your combining like term skills so that you have a better base for when we start to solve equations.